Now, we have already learned about fission reactions, and in this video we're going to compare fission reaction to this process we call radioactivity. Fission reactions, remember, is when you have a nuclear change in which the relatively unstable nucleus is broken into two nuclei of about the same size, but not exactly the same. Whereas radioactivity, this is a spontaneous change in which unstable nuclei decay. Okay, so that's what we're going to look at first. Now, we've seen these nuclear equations, and what we've learned is that mass number and nuclear charge are conserved across the change. So this first equation right here is a classical fission reaction, where we've got your uranium-235 nucleus. We bombard it with a neutron that has moderate kinetic energy, and then the uranium-235 breaks into two new nuclei, in this case barium-141 and krypton-92, and then emits three more neutrons plus energy. All of these particles then are carrying a great deal of kinetic energy. Now, radioactive decay is an example right here. This is where uranium-238, which is an unstable isotope, spontaneously spits off a little bit of its nucleus. In this case, it is a helium nucleus splitting off the uranium-238 nucleus to give thorium. Okay, so this particle is called an alpha particle. All right, and in this case, you can see carbon-14 splits off what is called an electron with high energy, and this is called a beta particle. Okay, and so you can see the difference between the fission reaction and the decay reactions, in which in the fission reaction, in order to get it going, you have to initiate the reaction by supplying some neutrons. In these cases, it's just a spontaneous decay. This spontaneous radioactive decay was first identified in the early 1900s by Madame Curie. She noticed that a sample containing uranium was giving off some kind of radiation. They weren't sure exactly what it was. They just knew that it was changing photographic paper. So just like exposing photographic paper to light would cause a change in the paper, exposing photographic paper to these elements in this rock, we're just doing the same thing. So Rutherford further studied it, and he classified nuclear radiation, according to its penetrating power. So that's where we get the alpha, the beta, and the gamma. The alpha penetrated the least. If you held a sheet of paper between the source and a detector, you could trap the alpha particles. So it penetrated the least. Beta particles were more penetrating. You need to put a book between the source and the detector. And gamma rays were the most penetrating. Gamma rays would go through the book and the paper, and it required lead, a sheet of lead, to stop the gamma rays. So that's how we ended up with the terms alpha, beta, and gamma. So what exactly are they? Alpha decay, for example, if you have a plutonium-240 isotope, it is an unstable isotope, and that plutonium will spontaneously give off an alpha particle. And an alpha particle is two It's a helium which contains 2 protons and 2 neutrons. So it doesn't have any electrons because it's spitting off of the nucleus. This is just a picture of the nucleus, and the alpha particle spits off. And because you're losing 2 protons in the process, you change the chemical identity to uranium-236. A beta particle is an electron. It's a high energy electron, an electron that has a lot of kinetic energy. And it's not an electron that is in the electron cloud around the nucleus. Here's an example with cesium-137 here. We're focusing on the nucleus of cesium-137, and it's an unstable isotope. It gives off a beta particle. And the source of this high energy electron, like I said, it's not from the cloud of electrons or outside the nucleus. It's literally a neutron is splitting apart. The changes into a proton and the high energy electron. The proton stays as part of the nucleus, and the electron is spit out of the atom altogether because it's got a lot of kinetic energy. So it's not an electron from the electron cloud. It's literally a neutron within the nucleus breaking into a proton and electron. So that's why when a nuclide undergoes beta decay, the nuclear charge actually increases, and so it goes from an atomic number of 55 to an atomic number of 56. So it goes from cesium to barium. Okay, and then gamma decay. Gamma decay is when an unstable nucleus just gives off electromagnetic radiation. So in a lot of the fission reactions and decay reactions that you've looked at so far, we haven't even put gamma radiation as in the reaction because there is no mass or charge associated with gamma radiation. It's just this high energy electromagnetic waves that are given off at the same time that other parts are given off. But sometimes you'll have gamma radiation given off by an unstable isotope. In this case, it's plutonium-240. Will give off gamma radiation. You still have plutonium-240. It's just in a lower energy state. So the nucleus itself is as unstable, has extra energy. It'll just give it off in the form of gamma radiation. Okay, so those are the 3 basic types of nuclear decay. There's other types, but those are the 3 most common types. All right, it's summarized here in this table, the 3 types of irradiation. Oh, I wanted to show you something before I show you this table. Let's look at a little animation. This is from your book. Here we go. First, we're going to look at carbon-14.
Carbon-14 spontaneously emits beta particles from its nuclei. Since beta particles are attracted to the positive plate of an applied electric field, they must be negatively charged. In fact, beta particles are electrons that are formed and then emitted from the nuclei of certain radioactive isotopes. In the decay process, a neutron is converted to a proton and a beta particle. A carbon-14 nucleus contains 6 protons and 8 neutrons. During beta decay, one of the neutrons is converted to a proton and an electron. This electron, called a beta particle, is then ejected from the nucleus, producing nitrogen-14. A nitrogen-14 nucleus is stable, thus no further radioactive decay occurs. Radon-222 is being formed continuously in our environment by decay of uranium-238. Radon, being a noble gas, is chemically unreactive. Therefore, it is not trapped by chemical processes in the soil or water, and is free to seep up from the ground and into homes. Radon spontaneously emits alpha particles from its nuclei. Since alpha particles are attracted to the negative plate of an applied electrical field, they must be positively charged. A radon-222 nucleus contains 86 protons and 136 neutrons. During alpha particle emission, a particle composed of 2 protons and 2 neutrons is emitted. An alpha particle is equivalent to a helium-4 nucleus. When an alpha particle is emitted from a radon-222 nucleus, a polonium isotope, polonium-218, is produced. Since an alpha particle contains 2 protons, the atomic number decreases by 2, from 86 to 84. An alpha particle has a mass number of 4, so the mass number decreases from 222 to 218.
Okay. And now this is just a table in your notes so you can keep track of that information and know what you're responsible for. So finally, I just wanted to bring us back to why we were talking about radioactivity in the first place. Remember we mentioned that, well, the nuclear fuel is dangerous, and the spent fuel is also dangerous. We're going to talk about why it's dangerous in video 6, but for now, you should know that the fuel itself is radioactive, and the fission products are also radioactive, which means they're going to be giving off alpha particles, beta particles, and gamma rays. So in video 6, we're going to talk about what biological effects this radiation has. But next, we'll go to part 2 of video 5 to learn about why some nuclei are unstable in the first place.